Let's go one step further and have a look at another question. This one says a 20-kilogram wagon is being pulled to the right with a force of 100 newtons at an angle of 30 degrees above the horizontal. What does that mean? Well, you guys have all pulled a wagon before, right? My son has a paper route. He puts his papers in his wagon and pulls the wagon like this. He doesn't get down on his knees and pull the wagon like this, horizontally, like this, even though physics-wise, that would actually be more efficient. Biologically, it wouldn't be. Anatomically, it wouldn't be particularly efficient. When he's pulling it like this, that's the most efficient way anatomically because it's easier for him to stand and walk. But physically, it's not the most efficient because when I'm pulling it like this, part of my force is pulling the wagon horizontally, but part of the force is also pulling it upwards. And I don't really want to pull the wagon upwards. I want to pull it just horizontally. Let's draw a little picture of this. Here's the wagon. We're pulling the wagon up like this at an angle of 30 degrees above the horizontal like this. We're going to label this one FA, or you can label it whatever you want, I suppose. FA is 100 newtons. It says there's a force of friction, 50 newtons force of friction acting on the wagon. Which way is friction going to act? Yeah, friction is going to act to the left, of course. So let's label that this way. And it's, of course, going to be parallel to the ground. It's always going to be parallel to the surface, right? What other forces do we have acting here? We've got gravity and normal force. Do they cancel each other out? No, they do not cancel each other out this time. Okay, we've encountered a few problems where they don't cancel each other out. Maybe the elevator problem they don't always cancel. The inclined plane they don't always cancel. This situation, we might think that they do because the object isn't accelerating upwards or downwards. Right? You pull the wagon, it moves horizontally along the ground. But yet, the normal force still doesn't cancel the force of gravity. Let's draw those two forces in now. There's the force of gravity. I'm going to start drawing the normal force, and I want you to tell me when I should stop drawing the normal force. I'm running out of space. Okay, oops, you missed it somewhere. I'm going to try again. Tell me when to stop drawing the normal force. Stop right there. Is the normal force smaller than gravity? How come? Because I'm pulling upwards as well. Yes. So we've got in this situation really an x component of this applied force, and we've got a y component of this applied force. And really what we've got going on here is that the y component is helping out the normal force. It's kind of like the buoyant force, right? When you're trying to lift a rock in water. You lift that rock in water, it's easier to lift it. Why? Because the buoyant force helps you lift. Well, in this situation, the normal force has to lift up, has to counter gravity, but not quite as much because you're helping it. When I apply that force at 30 degrees, I'm helping the normal force pull up there, right there. So, in the end, that's not going to matter a whole lot for this particular question. The question down the road, maybe it does matter that the normal force and y component cancel gravity. Okay, but in this one, it's not the end of the world. You're probably going to get away with it if you don't notice that. What do you want to try next? After we've got our free body diagram drawn here. Five words should probably come to your mind right now. Yeah, the x and y components. And why do we do that? Because, 5 words, I don't like funny angles. Okay, we got a 30-degree angle. Back to this now, right? We got a 30-degree angle. We don't want a 30-degree angle. So let's resolve that into x components and y components. Cosine 30 degrees, you guys know how to do this, right? We've done this a million times, is equal to the adjacent side over the hypotenuse. The x component ends up being 86.6 newtons. And the y component is the opposite side. So we're going to say sine 30 degrees there is equal to Fy over 100. And Fy is equal to 50 newtons. Let's just kind of square that off so it's off to the side. Thank you. Now, if we want to, we can just get rid of this, right? Get rid of this 100 newtons. Doesn't exist anymore because we have an x component that's equal to 86.6 newtons and a y component that's equal to 50.0 newtons. Still looks a little bit ugly, but if you remember that gravity does not cancel with the normal force, but rather cancels with the normal force and the y component, both of those combined cancel gravity, then it looks like all I've got left here is two horizontal forces, the force of friction and then the x component of my 100 Newton applied force. And now it's just like one of those questions that we did a few weeks ago near the beginning of this unit. F net is equal to the sum of the forces. We're going to say FF plus FX. What's the mass of this thing? 20 kilograms times the acceleration equals negative 50. Still, even on the quiz today, still a few people forgetting the negatives and positives, right? Okay, left negative, right positive. Negative 36 on the right-hand side divided by 20 gives me 36 divided by 20 would be 1.8, 1.83, which we're going to round to 2 digits. So we're going to say it's positive 1.8 meters per second squared. So if I pull that at 100 newtons horizontally, if I pull it with 100 newtons horizontally, is it going to accelerate the same or more? More. But the problem with pulling a wagon 100 newtons horizontally versus 100 newtons at an angle is that you can't really do that, right? Because of our anatomy, we're too tall to do that, right? If we pull it horizontally, all of our force goes into moving it to accelerating it, but we can't pull as strongly if we're pulling it just horizontally. It's kind of like back in projectile motion. Back in projectile motion, physically, like physics-wise, what would be the optimum angle to throw a ball if you wanted to maximize the distance? 45 degrees. But anatomically, it's actually more like 38, 39 degrees because you can't, like anatomically, you can't really throw it very well at 45 degrees. So if you can throw it with the same velocity at 45, that's better. But the reality is you can throw it harder at about 39, 38, 39, 40 degrees. So physically, it's one thing. Anatomically, it's another thing. We good there? What's different about this question versus those questions we were doing earlier on in the unit? Well, we got that funny angle, right? So we get rid of that funny angle because we don't like it. Get an x component and a y component. And the y component mysteriously disappears. Not so mysteriously, really, right? The y component disappears because this is the important thing in this one, the y component, along with the normal force, both upward forces, they have to cancel the downward force of gravity. So that's I believe, the third situation now we've seen where the normal force does not cancel gravity. All right? Make sense? Worksheet going out right now with 2 questions on it. I'd like you to take a look at both of those questions, please, over the next 5 to 10 minutes. All right, let's have a look at question 1 here. It says calculate the acceleration. It's just like the example question, except that in the example question, we also had friction. That doesn't change things a whole lot. It actually simplifies this one a tiny little bit, but not very much. Okay, in the end, what do we got to catch here? Well, we got to catch the fact that we've got a funny angle, and we got to get rid of that funny angle. So let's do that. Off to the side over here, we got 30 newtons at a funny angle of 30 degrees. So let's resolve that. Let's draw in my x component and my y component. I'm going to call this fx and this one fy. Let's say cosine 30 degrees is equal to adjacent over the hypotenuse. So what is fx equal there? 30 times cosine 30 is going to give me 25.98. Thank you. And then we're going to say sine 30 degrees is equal to the y component. This is the opposite side of the triangle. So we're going to say Fy ends up equaling 15 newtons, I think it is. Let's box that off to the side there, right? Whenever we see that funny angle, we get rid of that funny angle. Now, I don't want to say the exception to that, but we treated inclined planes a little bit differently, right? Remember, we had that funny angle, maybe the hill was at 30 degrees or 40 degrees. We didn't resolve that in the same way. And the reason we didn't is because it was moving that way, right? You're applying a force at the same angle as it ends up moving. Like really, when you had that inclined plane, yeah, we had a funny angle of, say, 30 degrees, but if you just kind of for a second, it's not what I want to do. If you just kind of for a second visualize it like this, then we don't really have a funny angle, right? Like the motion is all along that angle. So there was a funny angle of 30 degrees in those inclined planes, but the reason we didn't treat it like we treat every other funny angle is because, as I say, the motion is along that angle. Okay, we can think of it if we want to twist it around to be horizontal like that. All right, so what do we do now? Let's draw our free body diagram. We've got one force of 30 newtons, but I'm going to replace that with a force Fx equal to 25.98 newtons. And I'm going to replace it with Fy, which is 15 newtons. Now we also have a force of gravity acting down, and we have a normal force acting up. Tell me when to stop drawing the normal force, Mallory. Can you tell me when to stop drawing the normal force, roughly? Yeah, somewhere around there. And we stop drawing it there because that normal force and that y component combine to cancel out this force of gravity. So the normal force can't be as big as the force of gravity, right? Well, the good news is, even though the gravity and the normal force don't cancel, gravity and normal force and the y component do cancel. So now I'm left with just one force. I'm going to say F net is equal to the sum of the forces, or F net is equal to the one force I have left, which is the x component. You say 10 times A is equal to 25.98, and I end up with an acceleration there of about 2.6 meters per second squared. Good. How is that different in question 17? It's the same numbers, right? Except we have friction. So what else would I put in here? I got to make sure that I have friction drawn like this, right? Its value is 15 newtons. So in this question 17, I would add friction in there. And the force of friction would be negative 15 newtons, right? So what does that become? About 1.1, I think. Is it 1.1 meters per second squared? Is that good? Let me show you one more thing here. We've got our wagon again. This is kind of the class of problems. I call it the wagon problems. Right? It's not always a wagon, right? It doesn't have to be a wagon, but that's what I usually call them, as wagon problems, because that's probably the most common situation where you're pulling something at an angle, right? But yet it moves horizontally. So we call it the wagon problems. Okay, we got an applied force here, let's say of 200 newtons, and let's make our angle 30 degrees again. This time, instead of having a force of friction given to me, this time we're going to have a coefficient of friction given to us. Let's make that coefficient of friction 0.20. Let's make the mass of our object 30 kilograms. How does this change things? Actually, let me draw that coefficient of kinetic friction over here, just so we have room to draw our gravity and normal force. How does this change things? Well, not a whole lot, actually. We're still going to go over here and get rid of that 200 Newton force at 30 degrees because we don't like funny angles. Let's draw in our X, let's draw in our Y. Let's say cosine 30 degrees is equal to adjacent over hypotenuse. And I think that works out to be 173.2. The y component, sine 30 degrees, because it's the opposite side. That's a nice easy one. Fy is equal to 100 newtons, I believe. Square that off. And if we want to, like I usually do, let's replace this now with an x and a y. We have an x of 173.2 newtons and a y of 100 newtons. Good? Yeah, so far it's not one bit different than the other three questions that we've done on this stuff so far, right? Not one bit. It is going to become a little bit different, but we'll see what that is in just a moment here. What are the forces that we have acting here? Gravity and normal force, all right. So let's say gravity is acting down, and I'm not even going to bother asking you this time. We know the normal force acts up, and we know that it's smaller than gravity, right? Anything else? Gravity and normal force and Fy cancel, yeah, but there is one more force acting before we worry about canceling anything else. Friction is going to act to the left here, right? So let's draw that in. Force of friction to the left. Now, Bruce, you're right. Gravity, normal force, and the y component end up canceling each other out, right? So we're left with two forces, but we don't know what the value of friction is. How do you find friction? Oh, good, good, good. Let's say we want the force of friction, right? Force of friction is mu times the normal force. Agree? But I don't know what the normal force is. So let's get that. How do we get the normal force here? Well, you just told me, I think, Bruce, that the force of gravity acting down is equal to the normal force and the y component acting up. Does that make sense? The downward force, which is just gravity, equals the upward force, which is the normal force and the y component. So we're going to say gravity is what? 30 times 9.81 equals the normal force plus Fy, which is 100 newtons. So what's that? 294.3. Take 100 to the other side. Fn equals 194.3 newtons. Well, now we can find the force of friction. Is 0.20 times 194.3 newtons, which is 38.86, I think. 58? No, I think it's 38. I think. Now we can start saying that whole F net is equal to the sum of the forces thing. We're going to say FF plus Fx. We're not going to account for Fy and Fg and Fn because they cancel, although we did need to use those values to find out what the normal force was to get friction. 30 times A equals, friction is negative 38.86. The x component was positive 173.2 newtons. And we're going to solve for acceleration. When we do, we end up getting 4.5 meters per second squared. What makes this question different than the last question? The coefficient, obviously, and having to deal with the normal force and recognizing, not remembering, but recognizing that the normal force is not just m times g. It almost always is for us, right? 30 times 9.81. but this time it's not 30 times 9.1 because it's being helped by the y component of my applied force. Here's another one that's not in your book, unfortunately. We want to find the net force acting on this one, where we have, oh goodness, it's 20 newtons being pulled in 3 different directions. One is straight north, one is straight east, and the one is 20 newtons at 30 degrees south of west. We're going to come across a bit of an issue for this one in a second here. What's the first thing you want to do with this? We have a free body diagram drawn already, right? If you don't have a free body diagram, then draw the free body diagram, but we've got it here. So what's the first thing we're going to do if we're already given that free body diagram? You know this. Even though you might not know how to solve this problem in its entirety, there's something that you can look at in this and say, oh, I know what to do with that. Get rid of the funny angle. Okay, I got an angle of 20 degrees, sorry, 30 degrees. Let's get rid of that funny angle. So let's do that over here. There's our angle, 30 degrees. There's our hypotenuse, 20 newtons. And then let's draw in the x component and the y component. Let's say cosine 30 degrees is equal to x over 20. And let's say sine 30 degrees is equal to y over 20. Now I can, if I want, redraw this, right? And that's what I want. I'm going to draw an x component right here of 17.32 newtons and a y component right here of 10 newtons. Let's just scratch that out right there. Because I don't want that there anymore. Right? We get rid of our funny angle. We don't like funny angles, we get rid of it. We replace it with a 17 and a 10, so why do we need that 20 newtons in there now? Any ideas now? Do things cancel here? Like if things cancel, then we should get rid of it, right? We have a force of 20 to the right and 17.32 to the left. Do they cancel? No. We have a force of 20 up and 10 down. Do they cancel? No. So what are we going to do? X and Y components. If you don't have these things canceling, then we've got to do X and Y components. Okay, just like we did back in Unit 1, back in our kinematics unit with displacement and velocity vectors. We got X and Y components. So let's add them up. The X components, let's say, well, let's call this one the first one, second one, and the third one over here. The X component of the first one is 0. The Y component is 20. The second one, the X component is 20. The Y component is 0. The third one, the X component is negative 17.32 because it's to the left. And the Y component is, some people like to say 0 and then go to a fourth one. I just like to say it's negative 10. Okay, the green one, the third one, even though I have it drawn as 2, I like to just do it as 1 there. Whatever works for you, though. Okay, we add these up. This is going to give me 2.68 newtons, and this one's going to give me 10 newtons. What's my answer here? 12.68? Can't. I mean, you got to add these together, but you're not going to add them together that way. Okay, that's the grade 1 rules of addition, right? 10 plus 2.68 is equal to 12.68. So what are we going to do there? Shay, what are we going to do with those two vectors? Yeah, put them together, y and x, a triangle, right? So let's say we have 2.68 this way, and we have 10 newtons this way. My resultant vector is drawn from start to finish. And we'll draw theta in there at the very beginning here. So r is equal to 2.68 squared plus 10 squared. Theta is equal to the inverse 10. It's been a little while since we had to do this, of 10 over 2.68. What do we end up getting for r there? 10.35. We're going to round that to, actually it should technically be rounded to 10 newtons, right? 2 digits. And theta is going to be 74.9. We'll make it 75 degrees, and that would be north of east. Boy, it's kind of coming back to Unit 1, right? If you did well in this stuff in Unit 1, like you're going to ace this stuff here. If you didn't do well, then. All right, now you got a second chance to relearn it. I love it when I give you something like this that seems completely different than anything you've done before, and then there's some people that recognize that, wait a second, it isn't different than stuff we've done before. It's exactly the same, except my units aren't meters. My units are newtons. Okay, this question, if I had said, guy walks 20 meters to the north, then he walks 20 meters to the east, and then he walks 20 meters at 30 degrees south of west, you would solve that problem. In exactly the same way as we did here, except that you would have meters instead of newtons everywhere, right? Let me give you another one here. Let's say we got a bag of Halloween candy here. Doesn't look like a bag. It looks more like a ball. It's full. It's so full, in fact, that this bag of Halloween candy has a mass of 20 kilograms. You better have your wagon when you're pulling this one, because that gets pretty heavy, about 44 pounds, yeah. But remember, when you're pulling your wagon, remember that it's the normal force and y component combined canceling out gravity, right? Bring your calculator with you on Halloween night. This is such a great bag of Halloween, and lots of people want it, right? You collected it, but everybody wants this bag of Halloween. Not only is it 20 kilograms, but it has the full-size chocolate bars in there. Someone was giving out cans of Coke in there. Yeah, lots of good stuff in there. Everybody wants it. Everybody wants it to the point where somebody pulls it this way. We're going to call this the first person. Okay, person number 1 pulls it this way with a force of 100 newtons. Person number 2 pulls it this way with a force of, let's make it 50 newtons. Person number 3 pulls it this way at an angle of 30 degrees right here with a force of 70 newtons. And we're going to say person number 4 pulls it this way with a force of, we're going to make that one 60 newtons at 60 degrees. The question is, what is the net force acting on this bag of Halloween candy? Now, that's assuming that the bag of Halloween candy doesn't break with that net force, right? Okay, maybe it breaks because it's being pulled in all these different directions. But assuming it doesn't, and people don't go flying, and the candy doesn't go flying, what's the net force on this bag of Halloween candy? All right, let's have a look here now. Listen, we've got 2 funny angles here, so let's get rid of both of those. Let's draw the first one 60 degrees right here. 60 newtons. So let's draw our x component and our y component there. This is y, this is x. Let's say cosine 60 degrees is equal to x over 60. What does that equal? 60 times cosine 60. I think 30, isn't it actually? 30 newtons. Let's say sine 60 degrees is equal to y over 60. What does that equal? 51.96 newtons. All right. I can redraw that right now if I want. I've got a force of 30 newtons to the left here, and I've got a force of 51.96 newtons up. Okay, good. Let's do the other one now. 70 newtons at 30 degrees. Let's say this one is, actually, let's do this one in red. Usually I do it in green, but let's do this one in red just to distinguish it here. This is going to be X, this is going to be Y, and that's 70 newtons. So let's say cosine 30 degrees is equal to X over 70. What does that equal? 70 cosine 30, I don't know. 60.6. And then let's say sine 30 degrees is equal to Y over 70. Lightning fast calculation here. We get 35 newtons. Okay, let's box that one off as well. And let's replace this with a 60.6 and a 35. Now, it doesn't really matter. It doesn't really matter which one I draw first, but I'm going to choose to draw. No, never mind. I was going to say I was going to draw the Y component first to avoid overlap with the 30. But if I draw the Y component, then I'm going to overlap with the 50, right? So it doesn't really matter here. Let's say 60.6 newtons to the left, and let's say 35 newtons downwards. Now we can do this, right? Now we've got all X's and all Y's. So let's break it up into our X and Y components now, right here. Let's say the first one is 100 newtons to the right, 0 newtons up or down. Second one is 0 and negative 50. The third one, the red one, is negative 60.6 and negative 35. And the fourth one, the green one, is negative 30 to the left and 51.96 upwards. Okay, add these up. 9.4, I think, for X. And what's this one going to be? 85, 33.04. Is that what it is? How do you deal with this now? Redraw, right? 9.4, 33. You can do this. Hey, I got a question for you. In this one, I'm asked to find the the force, right? You can find the force with the Pythagorean theorem and the inverse hand function. What if I was looking for the acceleration of this bag? What if I wanted the acceleration? What would I have to do now? I'll give you a hint. Not much else. What's the one more step I'd have to do after I found the value of R and theta? Yeah, Emily? Sorry? F net, yes, but F net is equal to what? I'm sorry? M times A, good. All we're going to do to find the acceleration is say A is equal to F over M. Right? This is F. Well, both of those are F, right? The force is whatever it is at whatever angle divided by the mass, and that gives me the acceleration. Acceleration will be in the same direction, right? Good. Finish that off tonight if you haven't finished it off already. Have a good night, guys.